Okay, today, last of the conics. We've done circle, ellipse, parabola, now the hyperbola. This one is probably not often as used in the majority of our classes. You kind of already graphed one though a little bit. 1 over x, you could say, is basically a hyperbola. But some uses for a hyperbola. You guys talked a little bit about, or you read a little bit about a sonic boom. A hyperboloid is kind of the shape given to a nuclear cooling tower. A nuclear plant cooling tower was a shape that was kind of in a hyperbola. So anyway, we're not going to do a ton with hyperbolas. Yes, sir.
And Mr. Goodrich may join us.
Oh, okay. I'll get you to your definition here shortly. I want to show you what a hyperbola looks like first, talk a little bit about its characteristics, and then we'll go over the definition. For the most part, all we're going to do is graph it. Okay? A hyperbola really kind of consists of two curves, one out here and one out here. Sometimes those curves, instead of opening left and right, sometimes they will open up and down. Okay? You'll see some asymptotes here. Alright? Where those asymptotes meet, that is called the center of the hyperbola. Then, if this is the center, it's kind of like an ellipse. You know, on an ellipse, there's a major axis and there's a minor axis, right? Okay. So it's basically, you kind of think of it, it's very much like an ellipse, and we just kind of took the ellipse, cut it, and then took these parts and stretched them out back the other way. We just kind of inverted them, in a sense. Okay. So, just like this was a vertex for the ellipse, it's also a vertex for the hyperbola, except that part of it has been flipped over here, now is opening up to the outside. This part now is opening up to the outside there. Okay, so it's very much like an ellipse. You'll see with the equation that it's also very much like an ellipse equation. Okay, but so you got your center, you got two vertices, and you got two foci. And the foci are located inside the curves, kind of like with the parabola. So the focus will be inside that curve, and the focus will be inside that curve. Okay? So that's kind of what a hyperbola looks like. It is very much like the ellipse as far as the equation is concerned. You'll notice it's very much alike, but instead of a plus, we have a minus. That's how you can tell it'll be a hyperbola and not an ellipse, because everything else is the same. Alright? Now, I will say this, if the x value is the positive one and the y value is the negative one, so if x is the positive one and y is the negative one, the two curves open in the x direction. So the two curves will open like this. If it was switched, the y was positive and the x was negative, the curves will open more up and down. Okay? So again, you should be able to tell from looking at the equation that it's a hyperbola and whether or not it's opening up and down or left and right. Okay? So this is your general form for an equation for a hyperbola. Any questions on the values you see there? Or the equation you see there? HK is the center again, just like all the other ones have been. A is essentially half the length of the major axis. B is half the length of the minor axes, even though you won't really draw an ellipse, but everything kind of works the same. We'll do one here and you'll kind of get the hang of it. You do almost everything like you do for an ellipse, so they go hand in hand.
more. Yes, that one here. You may want to get some graph paper here. We're going to graph one together. If you just want to draw your own graph, that's perfectly fine too. Okay. Alright, so let's graph this one. Where is the center located? And be careful.
3, -2.
3, -2. Okay, make sure you give the x value first and the y value second. Okay, so our center is going to be at 3, -2. Okay. Because the y value is, I'm going to erase that, I need more room. Because the y value is the positive one and the x value is the negative one, which way will our curve be opening towards?
Up and down.
Up and down, yep. Okay, so there's my center, 3, -2. Just like with the ellipse, you will figure out your A and your B values, which are half the length of the minor axis and half the length of the major axis in a sense here too. If this were an ellipse, so if this was a plus right here, because there's a 9 underneath the Y, how far would you count from the center and in what direction?
3.
You would count 3
3
up and down, right? Okay, because 3 squared is 9, so my A value is 3. 3 squared is 9. I'm going to count that way in the Y direction, so 1, 2, 3 here. 1, 2, 3 here. Okay. How far would I count in the X direction?
2.
2. Okay, so right here and right here. Okay. Now, if it were an ellipse, if this was a plus, we would draw our ellipse now, right?
Yeah.
Okay. This is what we're going to do differently to help us draw our hyperbola. You're actually going to draw a rectangle right now, going through each one of those vertices. And the reason I want you to draw a rectangle is it will help you to draw the asymptotes for the hyperbola. Okay? The asymptotes will go through the center and hit the corners of the rectangle. So it'll look something like this. There's one of the asymptotes. There's the other asymptote. The asymptotes will hit the corners of that rectangle as well as go through the center. And now once you have the asymptotes drawn, you could draw the actual hyperbola. It will look something like this. You don't need to be specific with what coordinates it hits other than make sure it hits that vertex. And you guys told me already it's opening up and down, so I just drew the two curves, make sure they hit each vertex, have it open up and have it open down. There is the graph of the hyperbola.
How do we find the program?
Talk about that here in a second. Very good. We will find them. Yep, it's pretty simple. Okay? Alright, so here was my center at 3, -2. My vertices, there are only 2 of them. They were at 3, 1 and 3, -5. These are not vertices anymore, okay? I just used them to have us help us draw the rectangle. The foci will be located somewhere around here and somewhere around here, right? Okay? Remember on an ellipse, that A was the length, half the length of the major axis, B was half the length of the minor axis, and remember the foci fell somewhere right in here, and C was the length from the center to the focus, right? That was for an ellipse. And remember the relationship between A, B, and C?
A squared equals B squared plus C squared.
A squared equals B squared plus C squared in that instance, because A is going to be the largest value, and then using Pythagorean's theorem, A squared will equal B squared plus C squared in that instance. Okay? Here it's slightly different, because the largest value will be C. A is the distance from the center to the vertex. B is this distance. C is the distance still from the center to the focus. You see how C is the largest value? Everybody with me? Okay? So in this case, C squared will equal A squared plus B squared. The largest one is always one by itself, just like in Pythagoreans. Okay? So in this case, C squared equals 9 plus 4. So C squared would equal 13, or C would equal the square root of 13. So that means I would need to go the square root of 13 units up to get to the focus, and the square root of 13 units down to get to the other focus from the center. So my coordinates would be 3, -2, plus or minus the square root of 13. Because my center is at 3, -2, and then I need to add the square root of 13 to get to one focus from -2, and then I need to subtract the square root of 13 to get to the other focus, the one that's down here. So it's kind of my shorthand way of writing both coordinates. I just write them into one there. So I got my center, I got my vertices, I got my foci. And the one last thing I will ask you to write to are the equations of the asymptotes. Now, I'm a fan of using point-slope form when writing equations. You don't have to, but I'll show you why it's pretty nice to know that. It makes things pretty easy here. Both asymptotes pass through this point. And if you remember when we had our rectangle up here, we made sure the asymptotes hit the center and the corners, right? So I can count rise 1, 2, 3, run 2, rise 3, run 2, or from here, rise 3, run 2. So the slope of this asymptote would be 3 over 2. What's the slope of this asymptote? Negative 3 over 2, right? Down 3, right 2. So one of them has a slope of a positive 3/2, the other one has a slope of negative 3/2, and they both pass through the point 3, -2 in itself, okay? So I would write both equations in just one. So y minus
negative 2, so actually y plus 2, equals, one of them has a slope of 3/2, the other one has a slope of negative 3/2, so plus or minus 3/2, and then x minus 3, because my center's at 3, they both pass through the point 3, negative 2, excuse me. This is the point that I know both of them pass through. So I would just write my two equations using point slope form, knowing again that this is the point that both asymptotes pass through. So 3 is my x1, negative 2 is my y1, and then my slope, one of them has a positive 3/2 slope, the other one has a negative 3/2 slope. Okay, so that's what I would do to complete the equations of those asymptotes. If you do not like point slope form, that is fine. You can do slope intercept. You're just going to have to do a little bit extra work. Okay? If I was going to write the equation of this one right here, I can tell you that it has a slope of 3/2. So then you guys would write y equals 3/2 x plus b. You know it passes through the point 3, negative 2. So you'd plug in a negative 2 for y, you'd plug in a 3 for x, and you would solve for b. So negative 2 equals 3/2 times 3 would be 9/2, which is 4.5, because you guys would use calculators. You'd subtract 4.5 and you get negative 6.5 equal b. So y equals 3/2 x minus 6.5, and that is the equation of this asymptote right here. Then you'd have to go through and find the equation of the other asymptote as well. Okay, which is perfectly fine. You're welcome to do it that way if you're more comfortable with slope-intercept form. Okay, but I just think point slope is faster when all you have to do is write the equations. Slope-intercept is nicer to work with usually, like when you have to graph it or when you're solving systems of equations. Okay, but definitely when you're just writing the equations of lines, a lot of times all you'll know is a point and a slope, so it's just easy to put it into point slope form. Okay? Alright, so that is graphing hyperbolas. Very much like an ellipse, but instead of it coming together to make an oval, kind of like they're split and they're both pointed out in the other direction. Okay? What questions do you guys have before I close the video? Okay, there will also be problems similar to the other conics where I don't give you the nice form. You have to complete the square to put it into standard form. That's exactly the same as the circle and the ellipse that we've done.